Okay, well, so you can still hear me, I hope. So it's a great pleasure to be here on this occasion. Thanks very much to Don and the other organizers for inviting me and giving me the chance to speak as well on this splendid occasion. I must admit that I had considerable uncertainty, like some of the other speakers, I think, about what sort of talk I should give. And in fact, I'm still not entirely sure. In my case, I did get a specification from Don. And actually, this is the specification. So formal Methodists, as I've learned that they're called this morning, are supposed to be good at writing very clear and perspicuous specifications, but still not sure. Anyway, but really the range of even expanding out all these possibilities. I mean, the range of things I could talk about is very great, because it's very clear that LFCS, even before it existed, as I'll explain shortly, has been a major influence on me in all sorts of ways. And we've heard about many of these things, and many of the things I'll mention have been talked about by previous speakers, as quite to be expected. I'll just add my own perspective on these things. So it's been a major influence in shaping the community, something we were hearing about earlier that we're all working in, I in particular work in. It's been a major influence directly on my ideas and ways of thinking. And an important point, because a lot of this influence happened before I came to Edinburgh, long before, is as a kind of star to follow, a sort of beacon, really, that was establishing a way of doing computer science. And the great thing about having that is it's also something you can bounce off and do something different from. So one has the opportunity to add something to the mix. And I think that way of work that I did on game semantics and related topics, which began, in fact, before I came to Edinburgh and continued during the time that I was here. And I must say that sort of doing something that was a bit different, drawing much inspiration from ideas that have been developed here in Edinburgh, but also adding other things into the mix, more intentional kind of semantics, games ideas, linear logic ideas, and so on. So I received a great deal of support and encouragement from Robin, Rod, Gordon, and others at LFCS in following my own path, and that meant a great deal to me, and I'm sure that there are many other people who would say the same. So as I'm saying, there have really been many people and ideas in and around LFCS that have been important for me. Rather than trying to talk about everything, I just want to follow one thread in these remarks, just to give, particularly to focus on then 30 years ago and even more than 30 years ago and now, and where things are going now and into the future. So yes, before LFCS. So this was talked about. Of course, LFCS didn't emerge out of nothing. It emerged out of what was already a truly remarkable theory group that existed here in Edinburgh. And there are many key features about this, just to mention some that have always struck me. I think it's remarkable that such strong and distinctive scientific personalities and leaders, Rod, Robin, Gordon, and colleagues, could come together and cooperate so fruitfully and so well. That's not something to be taken lightly. It has enormous power, and as we've seen, has been enormously fruitful. And then, because of this critical mass, there was a development of a characteristic style, hard to define, but which we can all recognize, going along with a vision of the subject and a kind of scientific taste. And this was enormously important in raising the sort of whole level of one's conception of what a foundational study of computer science could be. And as I say, it wasn't just important here in Edinburgh, but it was a kind of inspiration and exemplar for others, both elsewhere in the UK and in Europe and internationally. And certainly this was the case for me. And it's hard to grasp now, perhaps, when the subject is much more established, how important that was then. The very conception of computer science as a serious scientific discipline, well, even now we could say, since I sit on committees with people from across physics and mathematics and so on, there's still work to be done in getting a wider appreciation of the depth and significance of ideas in computer science, but it was a lot worse then. And actually, even within computer science, you could find many voices to say that computing was a practical discipline only, it was a sort of branch of engineering, there was nothing much distinctive about it, intellectually that was all fancy stuff which was irrelevant, and so on and so forth. And having a strong and clear and inspiring example of a different kind was incredibly important. So I want to describe something that was particularly important for me. My first close encounter with the spirit of LFCS, which, as I say, pre-existed LFCS itself. And this was completely formative for me, so I therefore choose to focus on this and what we can discuss out of it. So having recently graduated, I did the conversion course at Cambridge, the diploma in computer science, as it was called. I joined GEC Computers working as a programmer, working on operating system development, which I actually rather enjoyed. And then the following completely chance event happened. The three lads who just graduated from Edinburgh, studying computer science, came and joined this company just outside London. And one of them was on the subscription list for the departmental reports. So, and these were the orange, we've heard about green booklets and orange booklets. So at this time, there were only orange booklets. And I came across two of these orange booklets on one of these, this guy's desk at work. Being a sort of browser, inveterate browser, I asked him if I could take a look at them. And these were these two reports, George Milner Robin, Concurrent Processes and Their Syntax, and a paper by Robin on flow graphs and flow algebras. So I don't know how many people here have read these papers. Some of you have, but not, I don't see many hands. Well, yes. So anyway, if as a consequence of this talk, anyone either is led to read or reread these papers, then I'll feel that the talk will have been worthwhile. I was looking at them again while thinking about this talk. They're actually, just as this was the period before LFCS, this was the period when Robin was working on concurrency before CCS. And these are two remarkable papers. I mean, they both appeared in JACM a couple of years later. Here's the quotation from the flow graphs and flow algebras. So notice Robin's impish sense of humor and the fact that he managed to get implicitly an expletive into JACM. It's actually a beautiful paper. It presents an algebra of nets and prove its completeness under a simple equational theory, so a prototype for many later results that were to come in the field of process algebra using the methods of initial algebra semantics. So it included infinite nets with these infinite numbers of wires. And an interesting point is that there are many pictures of nets in this paper. It's a precursor of many subsequent diagrammatic calculi, which are a big topic in current research, and of course figured a lot in Robin's subsequent work. So I could say a lot about that paper, but let me talk about the other paper a little bit. In fact, here's the quotation from the opening paragraph. Concurrency among computations which communicate with each other presents some of the most exciting challenges in the study of computation. Not only is it of great practical relevance, but appears to demand a theory of its own, which at present exists only tentatively. And here comes one of my themes, which has already been picked up on by at least two of the previous speakers, Bob and Jane. So Robin says one aspect of this theory must be quantitative, another, perhaps the other aspect, is qualitative. what conceptual framework is needed to understand and discuss the behavior of concurrent computations. Although these two aspects should presumably interact, and Robin could see that very clearly, of course, it appears to be sound methodology to separate them initially. And this paper deals with the qualitative aspects. And then here's this, the final sentence here is also very interesting, because he asks, what sort of a mathematical object is a process? What is interesting about this is that this was a question that Robin then decided not to pursue at least in the manner of this, this attempt. Because at this time, and this is one of the interesting points, Robin was using denotational methods, methods of denotational semantics and power domains and so on in this work. And then later he switched to operational semantics, with of course a major input from Gordon about structural operational semantics. And that really is what led to CCS and the calculi that we know. But Robin was very prepared to adapt the methods he used to the phenomena that he wished to study and what seemed best to fit the task at hand. So we heard about how he, at some point, eventually felt he had to resort to category theory and did so, of course, in a very original way. Okay, so there are several things I want to sort of pick up out of this, this discussion and see how they, again, then and now, how they, what is happening here, how it looked then, and how we might think about it now. So what I want to say is that ideas, I mean, the way that ideas flow, they follow their own course, which can be a sort of very intricate, of course, and hard to foresee. And the important thing is that we have to, I mean, the world changes, we change, ideas move along, and what is a fruitful guiding principle at a certain stage in the development of a scientific field doesn't always stay that way. So, I mean, one could give various examples, the kind of Machian analysis that Einstein used in the special theory of relativity. He then changed to a completely different point of view in his later work. But this principle of the separation of concerns that Robin referred to, the quantitative versus the qualitative, which was a perfectly deliberate step, which even was done in the knowledge that it was a preliminary step and ultimately things should be brought together, was immensely fruitful in its time. And this is really a big, I mean, this and sort of extrapolating to the wider sort of style of work done here, was a major part of this distinction that we've also heard about earlier today, distinction between Euro theory and US theory, or American theory, which Bob was also mentioning in his talk. And as we also say nowadays, track A versus track B theory, which has even been institutionalized in the ICALP conference. So I think the separation of concerns was an important and necessary step in its time, because there was every danger that not sufficient attention would be paid to these structural and conceptual aspects. But as was foreseen in that quotation, these two strands must eventually interact. And the interesting point is they are increasingly doing so. And again, we've heard two examples at least today of how they're doing so. In Jane's talk, where process algebra combines with performance analysis, and in Bob's talk, where semantics introduces cost notions. So one of the major carriers of this interaction, I think, has been the rise and increasing importance of probabilistic computation of various kinds, real-time weighted systems, quantum information, systems biology, computational game theory, and economics. One really can't any longer completely separate out quantitative and qualitative features, nor should one. And I think there will be more. Of course, persuading our track A colleagues to and people concerned with on the quantitative side to adopt also the structural tools is an ongoing discussion and challenge. So the second point I want to pick out is this thing about making computer science a serious scientific discipline in its own right, not just a service subject, an auxiliary, a branch of engineering. We take that for granted now, I think, and rightly so, but LFCS has played a huge part in getting us to the position where we can take it for granted. So one of the things that struck me when I looked at those booklets and just the spirit in which they were written, which was so different from anything I'd encountered before, whether in my sort of job as a programmer or indeed in anything I'd seen as a student doing the diploma at Cambridge, which was then still under the iron rule of Maurice Wilks, is this idea that the subject was really could be a deep enterprise in its own right. So there's this nice quote from a physicist, Percy Bridgman, the founder of so-called operationalism, which interestingly plays quite an important role in current work in quantum information and foundations, and where the spirit of it is not entirely, is quite related to the understanding we have of operational ideas in computer science. But he has this quote that science is nothing more than doing the damnedest with your mind, no holds barred. And that was the feeling that I had on reading those papers, which I hadn't seen before, and that was an important influence on me. So the picture looks different now. Computer science has arrived on the scene. Not everyone is cheering, but it's here and we're going to stay. But now, in fact, we must avoid remaining in splendid isolation. And actually, and more positively, lots of exciting things are happening on the boundaries with other disciplines. This is also something that Gordon was emphasizing in his talk. And I think in particular that the methods and modes of thought in computer science can and should be applied much more widely. And we're beginning to see that happen in some of the areas that I mentioned, biology, game theory, quantum information, and so on. Again, it's an ongoing struggle. I'm not going to rehearse my battle stories from conferences such as LFCS, whether being on the PC or being on the receiving end as an author, but as we all know, the idea of what should be in the scope of computer science conferences is still the subject of an ongoing debate. But I think overall, LFCS is a good example, the LFCS conference, Symposium on Logic in Computer Science, which has remained broad and taking in new material, although there's always been a certain line of argument that it should stay narrowly focused on a traditional view of logic. And the final point, which is striking to me, and again reflects my own experience, is the sort of question we can ask ourselves as theoretical computer scientists, people using mathematical methods in computer science. What do we need to know in order to do this subject? And one of the sort of salutary effects of reading those booklets all those years ago on me was that I realized there was an awful lot I'd never even heard of, never even heard referred to in my diploma that I'd taken at computer science was being freely used in these papers by Robin. So there was domain theory, there was algebra, universal algebra, and similar things. And so it kind of defined a syllabus for me. And then later I learned domain theory the hard way, and I mean really the hard way. This wasn't, by the way, from Gordon's lecture notes on domain theory, which I only acquired later. He gave me a copy, in fact, and I visited him in Edinburgh the first time. I actually originally learned domain theory by reading papers like A Power Domain Construction and some of the LCF as a programming language and the category theoretic solution of domain equations. That is definitely the hard way, but the only good thing about that is once you've learned it that way, you're not going to forget it. But this is how it looked back then. I even wrote down, I remember at some time, a sort of syllabus for myself of all the things one apparently had to know in order to enter this field. So there was logic, there was order theory, domains and lattices and so on, universal algebra, some topology of the point set variety, and then increasingly category theory. This is what we would still to a large extent think of as the typical mathematical background for doing track B or theoretical computer science or Euro theory. And there was a clear move between all of this and mainstream mathematics. which basically means what most mathematicians would regard as mathematics. And this is related to the previous point about the separation of the qualitative from the quantitative, because of course this is the mathematics of quality, and the mathematics of quantity is analysis, linear algebra, and a lot of other things. So it seems to me that this is perceptibly changing, and the range of mathematical methods are broadening all the time. And just to quote my own very much modest and call-by-need experience just from working in the area of quantum information and foundations, it's just not possible to avoid engagement with probability, linear programming, convex geometry, projective geometry, and so on, and the geometric side of topology, as well as the geometric and algebraic side of topology, as well as the point set side. And potentially there's much more. And of course, the really nice thing is that one looks at students now who move fluently among these different fields and acquire these different languages, these different mathematical facility with these different mathematical languages. So the subject is much richer mathematically than it was, and I think this is also a trend that will continue. Okay, so do I have a bit of time? 15 minutes, great. So, so having made these general remarks, I'd like to illustrate them by talking about some things I've been thinking about recently, which I think in various ways illustrate these themes, this progression from things then carrying forward the inspiration from that time, but also reflecting the way things are looking now. So reconnecting the qualitative and the structural with the quantitative, computer science interconnecting with other fields of science, both in the sense of being influenced by them, but also daring to try to influence them as well. And broadening the mathematical tools, connecting with, in some sense, the mainstream. So I don't want to get into technicalities, but I would like to illustrate this literally with some pictures to give an impression of some current work on contextuality, which is one of the things I've been particularly interested in recently. Actually, the first picture is just of some of my people I've been working with a lot recently, Rui Barbosa, Koei Kishida, Ray Lau, and Shane Mansfield. So contextuality is, I'm going to tell you all I need you to know about it in a moment, but it's one of the fundamental ways in which the quantum world and our understanding of the quantum world differs from our classical world picture. So it's something relevant to the foundations of physics. But it's also potentially a key resource in exploiting this quantum strangeness to achieve advantage over classical methods in information processing tasks. And this is really the main theme of quantum information. So it's quite a key topic. The slogan or mantra I would like to propose as a general way of understanding this, and once we see it this way, we can find it actually in many classical computational settings. So it pops up in constraint satisfaction of databases and elsewhere. So the mantra is contextuality arises where we have a family of data which is locally consistent but globally inconsistent. So what do I mean by this? Well, here's a first pictorial analogy. We're looking at some pictures of a structure. We take individual snapshots. Each one of them looks reasonable in itself, and they even look reasonable in terms of where they abut. Everything looks consistent. So this is the local consistency. So these different pictures correspond, as it were, to different. We have a camera with a limited aperture, and we're making our observations in this way. So this is locally consistent family of data. But what if we try and bring all this information together? After all, presumably there's an actual building there, which all these things are snapshots of. So if we try and put it all together, what should it look like? And actually, in this case, what we get is the famous Escher picture of the ever-ascending staircase. which cannot be realized in physical space. So it's really a kind of optical illusion. Interestingly, this picture was suggested to Escher to draw by Roger Penrose and his father, and the geometry that underlies this actually does relate to contextuality. But here it's just, we're just using it as an analogy. So I'm going to show you something that is, well, firstly, let me show it to you as computer scientists. So here we have some variables. You can just think of them as Boolean variables, and you can think of each row as expressing constraints on certain subsets of the variables. So in the first row, so the constraints on which assignments of values to the variables are deemed acceptable or possible. So on the first row, there are no constraints. Everything is okay. On the second row, these assignments are okay, but this one is excluded. On the third row, similarly, these assignments are okay, this is excluded here on the fourth row. It is an exercise which you as logicians, computer scientists, will easily undertake to see that there is no assignment to all the variables which satisfies all these constraints. Fourier, I think, has already worked it out. So, of course, from that point of view, it doesn't seem to be a big deal. But this is actually the essence of a famous construction in the field of quantum information and foundations, usually known as the Hardy paradox. So what is paradoxical about it? Well, now we should think that we are observing a system where we prepare a state, which you can think of as some state of entangled qubits, and Alice and Bob are making measurements. So Alice measures, so Alice has one of the particles, Bob has one of the particles. Alice measures for spin in a certain direction A or another direction A prime. Bob measures for spin in a direction B or a direction B prime. And what these constraints are now saying is these are the possible observations that Alice and Bob can make. And this is both what quantum mechanics tells us and what nature tells us, because people actually do these experiments in the lab. And this is what nature tells us. Actually, another interesting 30-year anniversary is that after 30 years of tests of Bell's theorem, the first generally accepted loophole-free tests, which even the most hardened skeptic will find difficult to argue against, were completed just last year. So this is real. And then the fact that there's no global assignment that satisfies all these constraints becomes very disturbing, in fact, very shocking, because usually, classically, we would think that fundamental physical quantities reflect real features of the physical object we're measuring, regardless of whether we happen to choose to measure it or not. The tree is still in the quad, whether or not we look at it. But what this is telling us, since these are real measurements and real observations, we can think of this more precisely as a sort of abstraction of a probabilistic information, where a tick means can happen, probability greater than 0, and a cross means can never happen, probability 0. So these are really what happens, and what this is saying is that it's just not possible to think of these physical quantities as having objective values independent of how we choose of what we choose to measure. In some sense, choosing the context of measurement brings these possibilities into existence. What does that mean? How to understand that? Nobody knows. The even more interesting question, perhaps, is what can we do with it? But what I want to show here is how we can see it, how we can visualize it in a topological way, which actually uses exactly the kind of structures which have been developed in the semantics of computation and very much in the spirit of LFCS. So I'm going to represent it in this way. We're going to have a base space, which is these variables that we're measuring. And I'm going to draw an edge between a pair of variables when they can be measured together. So therefore, when they appear as one of the rows in these constraints. So the point is, Alice can choose any measurement she likes, Bob can choose any measurements he likes, but Alice can only measure in one direction of spin at a time. So she can't do both A and A prime, but she can do any one of her choices with any one of Bob's choices. So that's our base. Above each variable in the base, we have a fiber which gives the possible outcomes, the possible values we can observe when we measure these variables. So in each case, this is 0 or 1. So these are the fibers. And now we're going to draw edges between outcomes in different fibers when they are possible together. When measuring in this context, for example, measuring the variables A, B, those two values for those variables could occur together. And you see on the first row, since everything is possible, we can draw 4 edges. But for the second row or the third row, only 3 edges are possible because we have these excluded cases here. So this is now a space fibered over this base. Now, what does local consistency mean here, firstly? Well, notice that this structure, this fibered space, this bundle, has the property that if I'm following an edge and I come to a vertex, then if I switch to another context, there will also be an edge incident to that vertex. So that's a simple, so I can always continue a path once I've started it. What does that mean physically? It's saying that whether this outcome is possible for this variable does not depend on whether I'm measuring it together with A or measuring it together with A prime. And that turns out to be a fundamental physical principle because Alice and Bob could be far apart. This is what's referred to as the no signaling principle. So locally, the possibilities are consistent in this way. This is what local consistency means here. Topologically, what does having an assignment to all the variables consistent with all the constraints means? It means having a path which runs through all the variables, a univocal path which comes back to where it started and which lives in the fibers. So here is an example of such a path that exists in this structure. So you see it's setting A to 1, B to 1, A prime to 0, B prime to 0, and this is all good. It's a univocal path, it meets itself, and this lives in this structure. But now the way in which this Hardy paradox manifests itself is, suppose we started somewhere else. Suppose we started with this local possibility. We know by local consistency we can propagate the path, but can we propagate the path in such a way that we end up back where we started? That we get a univocal path. So we can try, we can continue like this, and like this, and like this, but we haven't finished back where we started. We haven't got a consistent assignment of values. And we could go in the other direction, and again, we find that we don't get back where we started. So this is saying there's a certain local possibility which can't be accounted for by any global way of assigning values to all the variables. So this is the form of contextuality that we see in this structure. And this is all immediate from the topological structure. Here is another famous example which has an even stronger property. This is a famous example in quantum information known as the Popescu-Rorlich box, which actually shows superquantum correlations, in fact. So this is not something that Alice and Bob could see directly, but there are examples that could arise, according to quantum mechanics, that have the same structural property. And the structural property here is, no matter where you start from, you will never get one of these univocal paths. You will always come back somewhere different from when you start. And in fact, you can see that this is a kind of discrete version of a Möbius strip. So this may actually look, this may sort of be ringing some logical bells. And in fact, if we think of the classic liar paradox, and then people discuss liar cycles, where you have a chain of sentences, each one saying the next is true until eventually the last one says the first one is false, which we can think of in equational terms. Then we can think of them as giving a sort of, the point is now that these equations are themselves fibered over the variables they mention. Any subset of up to n-1 of these equations is consistent, but the whole set is inconsistent. And in fact, a liar cycle of length 4 corresponds exactly to the PR box. And the usual reasoning to derive a contradiction in the liar paradox by local propagation of values is exactly saying as you try and chase this path around, you can never end up where you started from. the tools that we're using here, I mean, this bundle structure, which we can also think of as a kind of a pre-sheaf structure, are exactly tools that have been developed in the semantics of computation, much of it developed here, but now applying directly to see the underlying structure of these examples that appear in quantum information. And in fact, we can take it a step further. There is real geometric content here, and we can apply cohomological methods to detect these obstructions to forming global sections and use them to detect large classes of contextual constructions from quantum mechanics. Okay, so this was by way of an illustration. So I guess I should be wrapping up, so I'll do that. So I just wanted to, it also occurred to me, I was also thinking about Kohei Honda, who John mentioned. And actually, Kohei spent 4 years in Edinburgh working with me, and we had a group of postdocs and students I was working with. We called ourselves the Interaction Group. So Kohei, Nobuko, Paul-André Méliès, who many of you know, Yulo Krobacek, who did his PhD with me here, and Jim Laird, now at Bath, who also did his PhD with me here. In fact, Yulo and Paul-André are both at PPS in Paris, now part of IRIF. Again, I was thinking of Kohei, and I hope Philippa will convey our thoughts to Nobuko. Okay, I'll there's lots more, as I was saying, I feel I could say, but I'll cut it short. So in sort of looking around, I came across this rather nice quotation by Francis Crick, which I think we could all take to heart. This isn't a picture of Francis Crick, this is Robin again, but notice the characteristic gleam of humor in his eyes. And Robin was certainly someone who worked extremely hard, but always found time for serious thinking. So again, I think his example can serve us all very well. So it's great to be here on this occasion, and happy anniversary, LFCS.